homework 10 is actually going to be our final required homework assignment. 10 final required assignment. This assignment is all written. There is no coding portion for this assignment. So, just keep that in mind. It's actually graded out of 30 points. And the 30 points, that's it. It's exactly 30 points. It's graded out of 30 points. And it's entirely written. So I expect all of you to submit this assignment on Gradescope. So we're going to go through the walkthrough. It's going to be a little bit shorter than usual, right? Our assignment walkthroughs are probably a little bit shorter. So this is going to be a little bit shorter of an assignment. But hopefully you guys can do these independently. If not, feel free to come to student hours, office hours, and also talk to me about it. So the very first thing we're going to do is I ask you guys to watch either a video here, this really good video resource that I've set up, or you can look in chapter 21 of our CLRS textbook. So the goal of the first part of the assignment is to teach you about a data structure called the disjoint sets data structure. Sometimes you'll also hear it called the union find data structure. This is a data structure that really allows us to leverage the Kruskal algorithm in order to very quickly find minimal spanning trees. So we're going to talk in detail about how that's done. And this is in preparation for later when I ask you guys to implement some of these algorithms and some of these data structures. So so part 1 is worth 0 points. I'm just asking you to learn a little bit more. It's probably going to take you, maybe 30 minutes to watch the video, and maybe a little bit longer because you probably want to take some notes, etc. So let's get started. Part 2 here really jumps right into where this data structure is used. So part 2 first starts by giving you an abbreviated version of Kruskal's pseudocode. So here's the pseudocode for Kruskal's algorithm. And if you guys remember from class, Kruskal's algorithm is an algorithm that helps you find the minimal spanning tree in a graph. So again, given a graph, you want to find the minimal spanning tree. That's what Kruskal's algorithm does. And in lecture, we talked about the general idea behind it, which is sort all edges by weight, where the smallest weight goes first. Then, look at each edge. If it does not create a cycle, add it to your MST, to your minimal spanning tree. If it does create a cycle, otherwise you skip it if it does create a cycle. And then at the end, return your MST. Not necessarily at the end, but just you can also check once you have connected all n nodes using n-1 edges, then that gives you a tree. And this is a little bit more detail. So this is actually so this is what we talked about in lecture. Here on the homework, I actually give you the actual pseudocode for how this would work. So the very first thing we assume is we have these functions called make, set, find, and union. So these are actually the APIs that the union find data structure exposes. So again, you need to understand what these functions are doing. So make set takes in a node x. However, we represent x maybe as an integer, as a node itself, and creates a new set that has just x in it, right? So in the backend, it does something to save information into x to be this is a new set. Then find takes in a node and returns which set it belongs to. And union takes in 2 nodes and combines the sets that they belong to into one big set. So if the 2 nodes are in the same set, it doesn't do anything. If the 2 nodes are in different sets, then it combines the 2 sets together into one big set that includes all of the nodes. And in part 3, we're actually going to go into more detail into these functions. So you're actually going to see one possible implementation of them. But for this part, you just need to know what the API does. And then we talk about the pseudocode for Kruskal's algorithm in a lot more detail. So the very first step is that for every node in V, so that's for every node in our graph, right? So somehow, there's going to be an API in our graph G to get the nodes or get the list of nodes. But for every single node in the graph, we want to make a set out of that node. So we're going to have n sets that have just a single node in each one, right? Then what we're going to do here is we sort the edges by weight. Again, so in C++, this would be like, calling standard sort on all the edges. And something that we don't talk about here in detail is that, when you sort the edges by weight, obviously you need a way to get the two nodes that correspond to the edge, right? So it's not just sorting the numbers. You would probably end up doing something, like standard sort, and then you give it the edges vector, and your edges vector is probably going to be something where it's like you have the two nodes, and then you also have the weight. So it's going to be like a triplet of elements, or a thruple, as some people tend to call it. But you're going to have a triplet here, where you're going to have the two nodes and then the weight. And then what you're going to do is you're going to say sort by, and you're going to tell it, sort by the third element in the thruple. And that's going to let you sort by the weight, but still have access to each of UV, right? And the next thing we do is we iterate over all the edges. And what we do is we call find on U and find on V. And like we said, find is supposed to return the set that U belongs to and V belongs to. And what we're checking here is if the set is not the same, so if they belong to different sets, then we add the edge UV to X, which is really the set of edges that correspond to our minimal spanning tree. That's X. X is going to be the set of edges that define our minimal spanning tree. And then we call union on U and V. So that means now you can imagine we have brought together these two nodes. And if this is not making any sense to you, feel free to take a lecture 32. There's a ton of diagrams in that lecture. So if even if you just open up the slides and you take a look, we have a bunch of diagrams for Kruskal's algorithm where it talks about how the sets get started and then how they slowly union into each other. Like here's an example where we're calling union here, we're calling union here, and then we call union here, and then slowly you start building up this one giant tree where at the end you have exactly your MST. And that's how the algorithm works. So for part 2, you get the setup, and then you're going to look at part 2.1. So again, for part 2.1 here, the very first thing that it asks you is just, we're just going to analyze this pseudocode. We're going to try to understand the running time of the pseudocode. So the very first question just asks you how many times will you call make set within Kruskal's algorithm. And I want you to put your answers in terms of n, which is going to be the number of vertices, right? So this syntax using the two vertical, the absolute value signs, when you give it a set, so this is a set of vertices, this means the size of that set. So we're going to say the number that corresponds to the size of that set is going to be n, and the size, which is the number of edges, is going to be m. And what I'm asking is how many times do we call make set? So again, if you just look at the algorithm here, you notice that make set is only ever called at the beginning, and it's called exactly n times. So make set is called exactly n times, right? For 2.2, we move on, and I ask, how many times do you call find within Kruskal's algorithm? So this is a little bit more interesting, I guess, because if you notice, find only gets called here in this line of code, but it gets called twice. You call it once for U and once for V. So there's a factor of 2. And it gets called for every single edge. So we actually always call find for every single edge in E sorted. So that's UV. So this would be 2 times M, because M is the number of total edges. You can imagine you can actually improve this running time, because once your set has n minus 1 edges, you will have completed. So again, like the big O is not going to matter, because in the worst case scenario, you won't add your last edge to the tree until it might be the biggest edge in the graph. It's just like you might need that edge in order to connect two parts of the graph. So you will iterate over the entire set E. So the big O running time is always M. So that's why this matters. But in the real world, you can imagine that you might, instead of just iterating over all the edges, you can very easily also add a check to see if the size of X is equal to n minus 1. When this is true, then you're done. So in the real world, you maybe, if you expect to have graphs that have a lot of edges compared to the number of nodes, you might get lucky. So if it's a very sparse, sorry, not a sparse graph, a very dense graph, so it has a lot of edges, it might be better to do this check because you'll probably find a minimal spanning tree a little bit faster than actually having to look at all of the edges. Now, of course, in the real world, it's like not super important as well because we did have to sort all of the edges. So sorting the edges alone is going to take you n log n time. Sorry, n. It's going to take you m log n time if you know nothing about the edges. But anyway, for 2.2, this expression is perfectly valid. So now we move to 2.3. And again, this just asks you how many times you call union. So if we notice here, again, we're trying to look not at the worst case running time, but how many times do we call union? And what you'll notice here is like at first, it seems like we're going to call union m times because we're iterating over all the edges. But notice that we only call union if find returns different sets. So in a way, union is called only when we add an edge to our MST, right? So only when we're adding an edge do we call union. And we know from class that the number of edges in a tree with n nodes is n minus 1, right? So the number of times that we call union is actually precisely n minus 1 times. So you might think we call it m times, but we don't because we only call it when we add an edge, and we will only ever add n minus 1 edges. For all of the other times that we are, in this for loop, the find u is actually going to be equal to find v. So it's actually going to return false, which means union is not going to get called. So this one's a little bit trickier than the others, but it's exactly n minus 1. And then the last part for 2.4, I just want you to describe in your own words why find u does not equal find b is the same as if this edge doesn't cause a cycle. And again, this is not super complicated, but if you think about it, basically, if two nodes u and v are in the same set, then they already have a tree spanning the two nodes, right? So they're already connected, right? It doesn't actually, you don't have to say that it's a tree, but I guess the main key is that if u and v are in the same set, they're already connected. So similarly, by contrapositive, if u and v are not in the same set, there is no path from u to v or v to u. Saying this is a little bit redundant because the graph is undirected. So paths don't have a direction. So obviously, if there's no path from u to v, there's no path from v to u, right? But this is the thing you notice, which is we keep the sets separate. We only add edges in our tree if the two nodes are not in the same set. So that is actually exactly the same thing as checking if adding this edge is going to cause a cycle. Because if the two nodes are in the same set, right? So that means this is they are equal, okay? Then they already have a tree spanning two nodes. They're already connected. So adding a new edge will create a cycle because the two nodes already, there's already a path from u to v, and now we're going to add, so this is a path. So it means there's some set of nodes that, take you from u all the way to v, like x, and then, that goes on, some nodes that exist. That already exists because if they're in the same set, we know that this must be the case because we would have only added them, the sets would have only merged versus a way to connect the two, right? So that's the thing that you need to notice. And then secondly, then that means if we add the edge, uv, this will create a cycle where you can go from u back to u. Yeah. So that's 2.4. Let's move on to part 3. Part 3 is a lot more interesting. So here we're actually going to dive into pseudocode for the make set, the find, and the union. Okay. So like we mentioned, there's code for the disjoint set functions. So looking at this code, we notice that make set takes as input a graph, a node x, and it makes a set out of it. So the way we are actually going to implement this in this pseudocode is we're going to modify the node to have two additional properties. a rank and a parent. So we're going to add a rank that is going to be set to 0, and we're going to add a parent, which is going to be itself. So basically, the way we're going to define a set consists of nodes that have ranks and parents. That's it. So again, this data structure is not super complicated to implement. It is very complicated to understand the running time of the data structure. But we're going to go into a little bit of detail for that later. Then what we'll notice here is we also have the algorithm for find. So this is makeset. Makeset is very simple. It should be obvious to you that makeset, this implementation of makeset is constant time. All we do is we add a rank and we add a parent. The find algorithm, it might not be so obvious to you what the running time is, but basically what we're going to do is given a graph node x, we're going to check to see if x is its parent. If x is equal to its parent, then we're going to return x, right? So basically the way find works is it says, if you are your parent, then return yourself, because you are the root of the set. Like you are the item in the set that represents the entire set. So whatever you are, you're going to represent the entire set. Otherwise, if you're not the parent, so if you have a different parent, you're going to call find on that parent and see like who is the parent. And the other thing that you'll notice is not only do we call find again to see who is your parent, after we figure out who is your parent, we're going to set your parent to, not figure out who's your parent, but after we figure out what set you belong to, we're going to directly set the parent of x to be that thing that we found. So this is going to become a little clearer later, but this is what the video, this is what we call path compression. So basically what happens here is if you have, let's say you have 1, and let's say 1 is the parent of 2, which is the parent of 3, which is the parent of 4, and you call, find on 4. So you give it 4. 4 is going to say, well, my parent is 3, which is not equal to me. So call find on 3, right? So this is going to call find on 3. Find on 3 is going to say, well, 2 is my parent, which is not equal to me. So call find on 2. Okay. 2 is going to say, well, 2 is not my parent. So call find on 1. Okay. And finally, 1 is going to say, well, so technically what happens here is like 1's parent is 1. So it has like a, self cycle to itself. So it's going to say, it's going to hit this last thing where it's going to say, oh, find of 1, I'm actually going to return 1 here, right? So calling find on 1 returned 1. And what you'll notice here is this function call, when we called find on 2, we returned 1. So we set 2's parent to 1, right? And then we also returned 1. So this also returns 1, and it sets the parent of 2 to 1. So that's fine. But now if you look at find 3, what that means is that find 3 gets 1 because we called find 2 here. So it's going to return 1, and then it's going to set the parent of 3 to 1. So again, we're going to return 1, but in addition to that, now we're going to have that the parent of 3 is 1. So 3 is now going to point to 1 instead of pointing to 2. And then similarly, when we return, when we called find 4, when we called find 3 inside the call to find 4, that's going to return 1. So it's going to set that the parent of 1, it's going to return 1, obviously, because 4 belongs to the set represented by 1. But it's also going to reset the parent of 4 to, instead of being 3, the parent of 4 is going to be 1. So now if you notice, you have a really wide tree. So instead of going 1, 2, 3, 4, we now have the 4, its parent is immediately 1. So the benefit of this is that next time you call find 4, it'll immediately know that the parent is 1. So it's going to call find 1, and that will immediately, find 1 will not call anything. It'll immediately return 1, which means find 4 will, return 1 with 2 recursive function calls, right? So instead of having to, climb down the tree because we rewired everything to point to the parent, the find calls using this path compression means that later calls to find are going to be very fast. Okay. So that's for find. Union is very interesting. It's not super complicated if you understand how find works. Basically, what it does is um, for union, if you call union on 1 and 2, or let's say we call union on 3 and 4 for our example above. The very first thing it does is it calls find on each one to see which set it belongs to. Obviously, find 3 here is going to return 1, and find 4 is also going to return 1 because they're already belonging to the same set. So what it does then is once you figure out which set they belong to, you look to see if the ranks, so let's skip this if statement. We're going to hit this else case. Oh, the pseudocode is wrong. Okay, so the very first thing it's supposed to do is if find x and find y are equal, so if x and y here are equal, the parents, the sets they belong to, there should be an extra if statement here. So actually, let me go ahead and add it. Apologies for that. That's a bug. So let me open homework 10. Let's look at union. Basically, what I'm saying is that here we should have a check with if x equals y. If that's the case, then we return. We do nothing, right? So we called find, and then if they're equal, we do nothing. If it already belongs to the same set, we're not going to do anything. So pretend that's there. So in this case, we would do nothing. Now, let's say 4 belongs to another set, which means it's going to return something like 2 or whatever. So, that means, let's say, 1 is the child of this, and then 4 is the child of this, right? So, 2 is the parent. So let me get my arrows straight. So let's say we had something like this, where 3 belongs to the set that has 1, and then 4 belongs to the set that has 2 as the parent. Then what we'll do is we'll check the ranks of x and y, right? So we'll check the ranks of 1 and 2. So obviously at the very beginning, if you guys notice, the ranks were all set to 0. So if this is the first time we're doing this, it's very clear that the ranks are going to be equal. So what we're going to do is we're going to set the parent of x to y. So basically what we're going to do is 2 is now going to be the parent of 1, who is the parent of 3, and then obviously 2 is also the parent of 4. So now we have this thing where if you call find on 1, it's actually going to return 2. If you call find on 4, it's going to return 2. If you call find on 3, it's going to return 2. So that's how we make them be part of the same set. And then also what we're going to do is if the ranks were equal, which is the case here, if x rank equals y rank, then we set the rank of y to be 1 more. We increase the rank of y to be 1 more. So we're going to increase the rank of 2. So now, 2's rank is going to be 1. Okay. And the intuition here is that if you'll notice, what we do is if the other statement is if the ranks are not equal, right? We hit this if statement here, which says, let's say the rank of x is bigger than the rank of y. Then we always set y, the parent of y, to be x. And what that means is basically if we ever union another set with 2 that has rank 0, it is actually going to become a child of 2, right? And the idea there is that the rank essentially, the rank is a proxy for how many elements in the set. And what we want to do is if we union 2 sets that are equal in size, then whoever became the parent increases its rank. So its rank goes up because now we've taken, like if I had 20 elements in one set and I had 23 elements in the other set, the assumption is their ranks are going to be equal. So now the new set has, 42 elements, but its rank is going to be +1. It's going to increase by 1, right? Otherwise, if we union two sets where one is smaller than the other, usually by a factor of 2, if that makes sense to you. So let's say, one set is 32, so it has rank 5. The other set is, 16, so it has rank 4. Then what's going to happen is this rank 4 guy is going to become a child of the rank 5 guy, and the ranks are not going to change. So now rank 5 is going to have 48 or whatever that works out to be, and it's still going to be rank 5, right? And the idea is that, again, the 5 is not like the fact that it's rank 5 does not mean it has exactly 2 to the 5th nodes, but it is an estimate where like eventually over time, you'll either join a bunch of smaller things to this guy, and then you'll get just one big set, or you'll end up joining two sets that are separate and are roughly the same size, and then that's when the rank increases. Okay, so that's how union works, and that's how rank works. So now let's actually jump into the questions, now that you guys have an understanding of that. So 3.1, suppose, it says, let's say we make the following sequence of calls. You have make set A, make set B, make set C, make set D, and then you have union CD, and then union AB, and then union BD. And what I ask is I want you to draw what the sets look like. Either it's a picture or a text representation after you make those calls. All right. So in this walkthrough, I'm going to do text representation, but you can imagine maybe trying to do, drawing the pictures as well. And really what I'm looking for is two things. We're looking for who's the parent. Who's the parent of each node, right? So obviously what's gonna, you have A, B, C, D. So you have A, B, C, D nodes, right? At the beginning, they're all gonna make their own set. So that means the parent of A, so this is how it starts. The parent of A, the parent of B, the parent of C. These are all going to be the same. So A's parent is going to be A, B's parent is going to be B, C's parent is going to be C, D's parent is going to be D, right? So that's just make set, that's the calls to make set. That's how it starts. Then we call union CD, right? So we're going to union C and we're going to union D. So C belongs to this set, D belongs to this set, right? So the rank of the two sets is both 0, right? So we're here. But they belong to different sets. So we're looking at the union. So they belong to different sets, but the rank is 0 for both of them. So we're not going to hit this if statement. We're actually going to hit the else. So immediately, we're going to set the parent of X. So that means we're going to set the parent of C to be Y. So immediately, C's parent becomes D, right? And then, because the ranks are equal, okay, so the parent of X and Y, the rank of X and Y, so the rank of C and D are both 0, we're going to increment the rank of Y by 1. So now the rank of D is going to be 1. The rank of D is 1. The rank of B is going to be 0. And the rank of A is 0 because it started 0. So that's what this looks like. And honestly, I might actually even drop this just to like draw it as a picture where we say, it should be clear that D and C both have the same parent given by D, whose rank is 1. Obviously, C still has a rank 0, but it's not going to ever matter again, so we can kind of forget about it. Then we call union AB. So a similar thing is going to happen again, where B is going to become the parent. So he's going to have rank 1, and A is going to become, a child. So both B and A both have parent B, whose rank is 1. And then finally, we call it union BD. So what that means is we're going to call union on B and union on D. So what that's going to happen is, again, the ranks are the same. So we're going to hit this statement here. We're going to set the parent of X to be Y. So we're going to set the parent of B to be D, right? So now this whole, so now the parent of B is D. And we still have that the parent of A is B, right? So we're going to have something like this. So A's parent is B, B's parent is D, C's parent is D, D's parent is D. Okay. And additionally, because the ranks are the same, we're going to increase the rank of D. So now the rank of D is going to be 2, right? And that is what, after all those calls, this is what the set would look like, right? So if you have this part for 3.1, we now get to 3.2, and it's going to ask you, hey, let's find x on the above. It takes multiple recursive calls. Then you call, oh, actually, this is a different question. So you call find x on the above. So you're going to call find on something. I don't tell you what it is, right? So the question is really, what is x? Okay. So what I'm telling you is that when I call find x, it's going to call itself several times. Okay. And that's because, again, if you notice, the implementation for find is if I am not the parent, I am going to call myself, right? Then what happens is you call find x again on the same node, and it's going to call itself fewer times, right? What is x? There's only one possible answer to this, which is, if you call find on D, it's going to call itself recursively. It's not even going to call itself recursively. It's just going to tell you, oh, the parent is D. Okay. If you call yourself on C, it's going to call itself recursively, and it's going to tell you, oh, the parent is D. If you call yourself on B, it's going to call itself recursively. It's going to tell you, oh, the parent is B. However, if you call yourself on A, so if you call find A, the first time it's going to call itself on its parent, so it's going to call find B, and then that is going to call itself on find D, which is finally going to return D. So this returns, this is going to return D, and you will return D. However, in addition to that, because you're resetting, in the find pseudocode, you're resetting your parent to whatever set you belong to, then A is now going to have its parent be D. So next time, the second time that you call find on A, you will immediately you will call yourself recursively on find D. So you're going to skip over B because your parent's going to be D, and that's going to immediately return D, which means you're going to return D, right? So the second time you call it, the number of calls you make to find actually decreases. And that's sort of like what we're looking at in 3.2. Okay. For 3.3 is what does the set look like after you make these two find calls, right? So we actually just went ahead and modified the set so it looks like this, right? So this is what it looks like now, because now A directly points to D. And then for 3.4, I ask you what the rank signifies. So we talked about that a little bit already, so I think you guys can probably tackle it on your own. All right, the next question is we're looking at part 4. So let's take a look at part 4. We're going to be talking about the ST cuts that we covered before. So an ST cut of a flow network is a partition of nodes into two groups, one which contains the source S and the other which contains the sink T, right? So you need S to be on one side and T to be on the other side, okay? So I give you an example here where I say figure 1 represents the cut SVUT. So that means S and V are in one set and U and T are in the other set. The cut capacity is the sum of all the edge capacities that go from the set containing S to the set containing T. So again, in this example, the cut capacity is 15 because we have an edge from S, from the set containing S to the set containing T. There's this edge for 7 here, right? And then there's this edge for 8. So 7 plus 8 is 15. Now note that the edge going backwards, so this is going from U to V, which is going from the set T to the set S, right? We don't count this edge. We only count the edges going forward, okay? That's the definition of a cut, and that's the definition of the cost of a cut. Now, question 4.1 just asks you to say, hey, there are 4 ST cuts possible in this graph. I want you to define all of them, right? So step 1 is find the 4 ST cuts, and I want you to give me the value of the maximum flow in this graph as well, okay? And you're going to have to use the max flow min cut theorem to find that. So first you list out the 4 ST cuts. So I already gave you one, which is this one. So SVUT is one cut. obviously, it should be pretty clear. There's another cut where S is by itself, and we have, U, V, T on the other side. There's another cut where we have S, U, V, and then T is by itself, right? And then you should be able to see from this drawing that there's another cut where instead of taking V to be an S, we take U to be an S. So the fourth cut is S, U, and then V, T instead of S, V, U, T. Now, I already gave you that the cost of this cut, the cut capacity, is 15 because it's given by 7 plus 8. But you can also look at the other cuts. So for the S cut here, you have two edges that are going to be going out, 7 and 1. So the cut capacity is going to be 8. For SUVT, you're going to have two edges going out. You have UT and VT going out. So the cut capacity is going to be 2 plus 8, which is 10. And then for SUVT, so that means F and U are in one set, and V and T are in the other set. You actually have three edges going out. You have this edge with 1, this edge with 3, and this edge from U to T with 2. So your capacity is 1 plus 2 plus 3, which is equal to 6. Okay. Now, by the max flow min cut theorem, that means that the maximum flow from S to T is 6, because that is the value of the minimum cut. Okay. So for 4.2, I asked you to verify this. All right. So 4.2 is for the maximum flow, which has value 6, right? Max flow has value 6. I want you to give me what is the flow on each edge. So for each edge, give me the flow and also explain to me why the max flow min cut theorem makes sense to you. Right? So again, looking at this, what that means is that for each edge, so you have the edge SU, you have the edge SV, you have the edge UV, and then you have the edge UT, right, and the edge VT. For each of these 5 edges, I want you to tell me how much flow in the maximum flow, which has value 6 total, how much are we pushing along that edge, right? So you can run the algorithm we covered in class. You can try to figure it out yourself. So I encourage you to pause the video and think about that. Take a look at the last problem in this assignment called negative prims. This is problem number 5, so part 5 here. And really what this is doing is we want to consider a similar algorithm to prims. So if you guys remember, prims algorithm is a different algorithm, very similar to Dijkstra's. That helps you find the minimum spanning tree, the MST, right? MST, and it does it differently than Kruskal, right? So Kruskal, so looking at this here, what we do is we don't cover what prim does here, but you guys can go look at the lecture. But basically, the idea between prim is to consider start at some node, doesn't matter which one. Consider all ways to add an unseen node from the current set of nodes in the MST. So at first you have some random node in MST, and then you consider all ways to add a new node to the current set of nodes in the MST that is connected, right? So at the very beginning, you would say, start with A, and then you basically, look at A's neighbors. And the idea is what you do is you add the node with the cheapest possible edge. And again, just to confirm this, like it's not pick some node and then add the cheapest neighbor, right? It's consider all edges crossing from the nodes you have already picked to the nodes that you haven't picked. So consider all those edges going across that cut. Take the smallest edge, right? And then keep doing this until you have added n minus 1 edges, in which case you will be done. So that's Prim's algorithm. And then what we do here is we actually didn't talk about this in class, but all of the examples we used in class had positive edge weights for the trees. So the question here that we ask is, does does Prim's algorithm also work for graphs with negative edge weights? And the answer is actually yes. It works perfectly fine. You can just directly use Prim's even if your graph has negative edge weights, right? You can actually just directly use it. But even if you're not sure, if you weren't sure, you might consider doing something like this algorithm that we see here, which essentially what it does for us is it finds the minimum edge weight in G. So if this is negative, it's going to be, like the smallest edge weight is going to be negative 10, right? So let's say we have a graph that's like A, with weight negative 10 to B to C, where C, uh, where C has weight, let's say 5. Then what this does is first it finds the minimum edge weight in the graph, so that would be negative 10. And then for every edge in the graph, it subtracts the minimum edge weight. So what does that mean? That means that this edge here is going to become 0. So it's essentially it will have the edge weight 0. So the edge is still going to be there, but its weight is going to be 0. So this is important. The edge is still there. Okay, it is still there. It's just the weight is 0. And then B would become 15. So this edge becomes 15 because you do 5 minus negative 10, which is 15, negative 10 minus negative 10, which is 0. And then what you do is you run prims on this algorithm, on this new graph. So now this graph only has positive edge weights, right? Either 0 or positive. And now you run prim and you try to find the minimal spanning tree, basically. And then what you do is you say, well, once I found my minimal spanning tree, which in this case, there is only one spanning tree. It is the graph itself. This graph is actually a tree, so AB. I'll update the edge weights on my minimal spanning tree to subtract the minimum weight, or to add the minimum weight. So this is going to be negative 10, and this is going to become 5. And then I'll return this as my answer to the original problem, right? So this just asks, give an informal explanation of why negative prim computes the correct MST, or find a counterexample where this algorithm will compute the wrong minimal spanning tree. You guys should really think about that on your own. I encourage you to pause the video, but the idea here is that subtracting weights from edges in a graph maintains MSTs. So, and really it's not even MSTs. It maintains the ordering on spanning trees. And why is that? That's because spanning trees all have exactly n-1 edges, which means that you are subtracting the same amount from every tree. So you don't have a case where some tree has more edges or less edges. So because you subtract the same amount from every tree, the ordering of the trees is going to be the same, which means the minimum spanning tree of one graph, if all the trees, that's the one with the lowest cost, right? If all the trees have their cost reduced by 50, then this is still going to be the minimum spanning tree in the new graph. So minimum spanning tree is still the minimum spanning tree in the new graph because all trees have their cost changed by the same amount. So unlike Dijkstra's algorithm, where you cannot do this to find the shortest path, in Prim's algorithm, you can. Cool. So that's the end for the walkthrough, and I hope you guys enjoyed it. Have a lot of fun with this homework assignment, and start studying for the